Okay, so without further ado, we'll introduce the next speaker, which is Nigel Smart. He'll talk about practical, robust MPC for Galois rings, and will hopefully make Galois rings understandable to the audience.
Okay, so the first thing is, I've got to stand here, shit. Right, okay, the first thing is we wanted to make the code and everything available for this meeting, but we just need to add a bit more help facilities, so it's going to happen in mid-April, and the document is about, so the code will be made available along with the document which explains everything in this talk, which will be about over 250 pages long. So in this 20-minute talk, I'm going to go over a 250-page document, right? So get ready. Right, so we're going to go fast. Okay, so in last year's Real World Crypto, I talked about how Zama was securing blockchains by encrypting stuff on the blockchain, and there was going to be a threshold protocol to do the threshold decryption and to do the threshold key generation, basically, and then said, that's just technical shit, you don't have to worry about that. This is the talk which does the technical shit, right? So that's what we're going to do. And it was all about rock stars. We're not doing rock stars this week, okay? So we didn't go into any details, so that's what we're going to do. Okay, so in some sense, you could kind of think of this, if you kind of think of a Lord of the Rings analogy, you know, like the whole point of Lord of the Rings is what's the point of the book? They could have just got the bloody eagles to do it in the first place. Okay, so you could just say, why don't you use a TE? Well, that's great, except TEs are hardware. We don't trust hardware. We don't trust vendors. And TEs are susceptible to side channel analysis. So if you ever want to talk about TEs, that's basically they're the eagles, yeah? You know, they're cheating, essentially. Right, so, but we are going to, the other problem with TEs is they're not elastic. HSMs are not elastic. So if you use software, it's a much more elastic thing for the cloud. You can spawn it better. We do use TEs in our deployment in Zama, but they're TEs which run the MPC itself. So we use TEs for defense in depth rather than TEs as the primary mechanism. Okay, so we have a fellowship. We have a precious item, the secret, and we want to keep it, so what we're going to do, we want to keep it secret, keep it safe, so we distribute it amongst a fellowship, or a group of entities, if you will. However, one of the fellowship could be evil. Yeah, that's Boromir. So so we've got to worry about the untrustworthiness of one of the fellowship. And in addition, sometimes someone goes AWOL for half the book, right? So we have to actually also worry about people dropping from the protocol as well, and then maybe coming back into the protocol. So this is kind of what you have with asynchronous networks. So we've got to kind of deal with the full Lord of the Rings plot here. Okay, but we want to be we want the fellowship to be successful. Okay, so on the face of it, this looks kind of easy. If we want to do FHE decryption, this is kind of easy. We just take the key, we thresholdize it, we run the decryption operation in the threshold. We have to run some bar noise thrusting or blah, 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 you know, kind of stuff. And it just looks kind of easy, yeah? You know, the key generation looks easy because it looks kind of vaguely linear. Even if you want to do NTTs, they're kind of linear. So everything's kind of easy. Okay, so it all looks trivial. Okay, so there's why a 250-page document. Okay, one does not simply apply. MPC will go on. So the real problem is that the ring is an extension of ZQ, where Q is a product of primes or a power of 2. So it's not a field. So all your MPC over fields, throw that out the window. We care about guaranteed output delivery, aka robustness, aka guaranteed output delivery, which is slightly different from the cryptocurrency. So when you kind of have crypto wallets really normally work in active with the vault setting, yeah? They don't work in robust setting. That's because if it's my crypto key, if I've got an attack, I've kind of got a backup anyway, and if I'm under attack, I want to know I've got on the vault and I can now go back and reinstall the software and access it. Whereas this key, if it goes down, everything goes down, yeah? So we need it to be robust. So unlike most MPC solutions, this is going to be fully robust, okay? And we care about asynchronicity because the internet's asynchronous, okay? We actually care about concrete efficiency because we actually want to implement this and deploy it, and we have implemented and deployed it. And we need to generate these LWE weird distributions like bloody Gaussians, so we're not going to we're going to get rid of Gaussians because they're just like shit, so we're not going to worry about them. But we do need to worry about these things. Okay, so there's all sorts of things you have to do. So you do not just use Shamir naively, right? So I can do my Sean Bean impression for the whole talk. Okay, so for those, you can read this slide if you want. So basically, when I said we're going to throw out fields, there's actually, we can go back to a master's thesis of Serge Fair from ETH donkeys years ago, which actually said how we can replace fields by rings in MPC protocols. It's all very easy. So instead of when you do your Shamir interpolation, you know, in textbooks you do it at points 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to n. What we do is we do it at points alpha 1, blah, 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 up to n, because, and these have to be from what's called an exceptional set. So to make this exceptional set, we might have to do a ring extension, but who cares about a ring extension because it's logarithmic in the number of parties. That's not going to be very much. And for BGV, that's 0 degree extension. But for TFHE, for when you have a power of 2, then this is kind of small, but the number of parties are small here. Okay, it's key. The number of parties are small, so we can throw out all that theory shit, which talks about asymptotics with respect to the number of parties, because that's a constant, right? So we actually really care about concrete efficiency. So a lot of the so-called efficient protocols in the literature really are efficient when n tends to infinity. So we're not, n isn't infinity, okay? Okay, so we do the Shamir, you kind of know Shamir. This is linear because Shamir is linear. So it is basically Shamir, but it's not over 1, 2, 3, 4, 5, etc. It's over alpha 1, alpha 2, alpha 3, etc., etc. Okay, so that's that's the Galois rings bit. Happy? You understand Galois rings now?
Sure, why
Why not?
not?
Yeah, okay. Okay, you don't just deploy maliciously secure protocols. Okay, so we need to consider other aspects. So a key point of MPC protocols is you open the secret sharing, yeah? So when you open a secret sharing, what normally happens if you kind of think of, like the active with aborts protocols with TS less than n/2, you kind of open it and then you basically apply error detection. And if you see an error, you go, and then you kill the protocol. That's essentially how they all work. Now, if you have TS less than n/3, you have this thing, the Shamir sharing is essentially a Reed-Solomon code. So what you can do is you can apply error correction, and that's how you get robustness on the opening protocol. And how does error correction work? Well, you can apply, there's kind of standard algorithms which work over fields, which are called Burley-Camp-Welsh, Burley-Camp-Welsh, or Gao, and they can be applied over fields. And generalizing these to the Galois ring setting is kind of trivial. It's you either kind of use Hensel lifting or use the Chinese remainder theorem. So this is kind of easy. You can kind of, you reduce the issue over rings to one over fields, and then you kind of bootstrap from there. So it's kind of easy. And then you basically have, we can do an error correction algorithm which works for the Reed-Solomon code. And essentially what happens is that we could do error correction bounds, and the usual things apply. But we have to worry about asynchronous networks. Luckily, there's an amazing protocol which goes back to the 80s, which is called online error correction. Okay, so there's the code there, but kind of what happens is you kind of values come in from all the different parties, and you want to open it. And what you do is you kind of go, yeah, have I got enough? And you can kind of, as they come in, you can kind of correct and kind of check and kind of then proceed when you've got enough. And so this is kind of like, so the online error correction allows you to do error correction when t is less than n/3 for asynchronous networks, whereas often when you have asynchronous networks, you kind of think you're going to get t is less than n/4. So there's a kind of nice little trick, only for opening. So opening is kind of easy, but if you've got kind of beaver triples and you want to do an MPC protocol, the online phase is effectively just opening anyway. So this gives us online phase robustness for free instantly, quite quickly. So that's kind of nice. We care about concrete efficiency, right? So we don't just get concrete efficiency. We don't just simply get efficient MPC just for nothing. So, okay, so we have two forms of MPC protocol. We have one for small people, little hobbits. Yeah. So if you have a small number of people, then what you can do is you can use PRSS. So this is kind of a way of getting secret sharing for free. So you basically press a button and then non-interactively, everyone can get a sharing of a random value for free. This is kind of like a standard construction in MPC. And this kind of depends on NT, the number of parties and the threshold T. T is going to be less than N over 3. So when this value is less than 10,000, which is basically, that's like 10,000 AES keys. So, so we can use the PRSS, we can use PRSS constructions to produce a efficient offline phase to generate beaver triples really, really efficiently. Then because we have PRSS, we can create, this is kind of like a new thing that no one's kind of seen before, because maybe no one actually bothered before. Really trivial, you can kind of get a very, very good dispute resolution on the offline phase. So if someone lies in the offline phase, we can recover from that and detect who did it purely by using the PRSS on its own, rather than having some complex backwards and forwards and whatever. So that's kind of nice and easy. So for this case, it's relatively simple, but we need a synchronous offline phase. We could get rid of that assumption, but we care about concrete efficiency. So in the online phase, we're fully asynchronous. The offline phase, we're synchronous only, but we don't need that so much. We only need the offline phase for when we're doing key generation anyway. But the offline phase is going to be expensive. I'll give you some numbers at the end. But that's when we've got small numbers of parties. That's the Hobbit MPC protocol. So if we have a large numbers of parties, we have ENTs. So this is like the big ones. Okay. So actually, when binom NT is large, a bit like an ENT, you can basically run the Damgard-Nielsen protocol. Okay. This is an ancient protocol from 2007. The extension to rings is kind of trivial. There's one little lemma you have to prove to make it work, and then, which is kind of trivial, and that's kind of easy. What we do is, for this, when n is large, we kind of only use it for t is less than n over 4. The reason for that is we could do t is less than n over 3, but then the dispute resolution framework is a bit more complex. And given that very few people are going to deploy MPC protocols with n equals 40, n equals 50, n equals 500, couldn't be bothered, really. You know, but the code is there, and we can run a DNO7. And the reason for using DNO7 as opposed to some of the more theoretical protocols is because on one case, DNO7, you kind of go, oh, that's not so good theoretically, is because it's got a statistical error probability, DNO7, as opposed to perfect error, which is some of the other ones, like the Thingy and Hurt paper has that. But what DNO7 has batch, so it's much more concretely efficient. Okay, so that's kind of the key. And the other point is it's super fast on the happy path. So on the unhappy path, where you have errors, but there, all the theoretical protocols are really talking about t is less than n over 3. So there's lots of work by Galois, which does very, very efficient asymptotics. But it's very efficient asymptotics. It gets rid of this order n squared term, but n's a constant, and we don't really kind of worry about that. So in terms of concrete efficiency, DNO7 is by far the most efficient protocol out there for offline phase for fully robust MPC protocols. Okay, and now we've got to do the LWE-friendly distributions with MPC. So this is going to be more technical, less high level, because it's a bit more funky. You may get something out of it, kind of. So, okay, so what we want to do is we want to generate bits. If we can generate random bits, then we're happy. So when Q is a power of 2, there's a paper by myself, and Manuela over there, Frey, and someone else who I've forgotten. I'm sorry, probably Dragos. Have I just insulted Dragos? Where's Dragos? Was it Dragos? Where are we? Was it with you? You think so? Okay. Anyway, we have this paper where well, it could be someone, I don't know. We generate bits. So when Q is a power of 2, we actually want to generate a bit. And so here's the code here, and that allows you to generate a bit in secret sharing. So you generate some random value, which is, if you're in the Hobbit protocol, that's just a PRSS evaluation. You now do a multiplication, do some shit, open some value, solve an equation, and you actually output a bit, which is kind of funky. And if you don't believe me, I've got an example on the right-hand side. And this basically works on the fact that essentially you've got like 2 roots of this x squared plus x plus v map. Yeah. So that's kind of, Q is power 2, it's kind of easy. When Q's an odd prime, it's also easy. There's an old result going back to, I think me, Peter, and Ivan and others did this in the Speeds 2 paper years ago, that you can generate bits this way by using the square root map. So you can do a similar thing, but that is only works when Q is a prime. If you run this for Q, a product of primes, you kind of get, the bits don't line up and you won't actually get a secret sharing of bits. But when we're in the Hobbit protocols, we've got a kind of trick that we use, which is kind of cute, which I thought I'd introduce here. So what we do is we do the same trick. So we got lots of primes. So we generate something which is a prime, which is a bit with respect to one of the primes. Well, it's a bit with respect to all primes, but there's a different bit with respect to each prime. So the CRT wouldn't give us a bit, yeah? But we take it as a bit with one prime, and then we kind of mask it using the fact we've got this PRSS, we can mask it, and then we kind of correct correct the error. So we're able to mask and then correct, which gives us a bit, which you kind of can read the code there, but it's kind of really trivial. So we're basically, if you kind of look at it, there's only 2 opens, and we can get a bit with respect to a product prime. So this gives us like dabbits, if you kind of know about dabbits, for relatively cheap work, but it kind of uses the fact that in a BGV system, we've got a big gap between the primes. So we use this for BGV key generation, and it's because we've got a product of primes. Yeah. Okay, so we could do that. We can now generate primes. We can generate bits. So given we can generate bits, we can now generate distributions. So for BGV, BFV, they kind of like, what they do normally is they don't use Gaussians, they actually use what's called the New Hope distribution. So that's trivial to generate from bits. Once you've got bits, you can generate the New Hope distribution. So that's kind of nice and easy. So that we don't need secure Gaussians for that. New Hope is like a Gaussian or not. For TFHE, it kind of needs Gaussian, it kind of seems to need Gaussians of large standard deviations. And if we use New Hope to approximate it, we'd need a gazillion bits to do that. But it turns out we're only using encryption. So we don't really need Gaussians. So we have this distribution which we call, it's a uniform-like distribution, which we call T-uniform. So it's a tweaked uniform, which is basically on the interval 2 to the minus b up to 2 to the b, and which is uniform on 2 to the minus b plus 1 down to 2 to the b minus 1. And then at the end points, it's kind of like a half of the probability you would have in the middle. So it's kind of, and the reason for doing this is it means that it's symmetric distribution, which is when you when you take averages and things like that, you still remain symmetric and you don't have to worry about skew. So this is all done. This is the standard distribution now in the TFHE library for noise distributions for TFHE, and it's also trivial to deduce from bits, because once you've got bits, voila, that's how you generate a thing. I've got a laser. Whoa, oh, whoa, that's funky, isn't it? Whoa, I like that. Whoa, look, whoa. Oh, well, we should have told us that. Whoa, that's cool. Right, anyway, I want one. Okay, yeah, so we can generate bits. Okay, so we seem to have reached the end of the plot, and we've managed to get, the fellowship has got its secret thing to generate threshold decryption. As I say, this is a summary of a 250-page document written by a large group of people. But you want some runtimes. So this is the decryption time of TFHE with a number of parties. when we're running on an AWS data center. This is the LAN setting, I think. That's right. Yeah, I think so. Yeah. It's the LAN setting. It's the LAN setting. If you have the message size, if you're decrypting 2 bits, 4 bits, 64 bits, it's basically the same. Who cares? And the number of parties doesn't increase very much. That's because there's this big squash operation, which is actually quite a big operation, which is a big computational operation we have to do first, which doesn't involve any MPC, but we can scale that over the 64 cores. So that's kind of nice and easy. So that is the threshold decryption time for 64-bit messages or whatever. So it's kind of funky, and obviously because it's MPC, we can horizontally scale. We can just spawn new parties in our data centers. So that's kind of nice and easy. And this is for key generation. I should have benchmarked key generation. So this is kind of funky. Is what we see is generating these bits is the pre-processing. So that they take hours, yeah? Which is kind of, but actually the time to actually generate a key, once you've got the secret shared bits, is in the minutes. And I should say is that this is unlike, you have these theoretical papers which do multi-key FHE. They cheat. Well, they don't cheat, they're just stupid, right? Because what they do is they kind of go, we're going to generate a key, and I'm going to generate a key, and you're going to generate a key, and then we're going to combine our keys together in some sort of FHE-like protocol, and then we get a joint key that we can now use. That's the wrong way to do it, because if you do that, the noise in the final FHE key is so much bigger, and that means you have a penalty when you do your FHE operations. So if you generate your key via an MPC protocol, you are guaranteed to get the same noise as you would have had as if an individual had generated it by themselves. So this enables us to have super fast FHE for just the cost of a few hours of key generation. But it's a few hours of key generation. I should say that we're generating hundreds of billions of secure bits here, so which is why that's why it takes hours. You know, we really need a lot of bits to generate an FHE key. If we used standard Gaussian distributions, it would be in the days or years, right? So the fact we're using these special distributions means that things are super fast. So there we go. There's some nice run times. That's a 250-page document in 20 minutes. Thank you. And there's some things you can contact. And as I said, everything will be available mid-April. They've now got to deliver, so they're going like, oh shit. Right, okay, thank you.
I'm going to ask you one silly question. If I move away from the, boy, I can't get out of here. You mentioned that one of your protocols requires t less than n over 4.
Yeah.
But then you also had n equals 4 for your.
Oh yeah, but t is less than n over 4 for when we're in the nth.
No, I understand. Right, but then you still need it for the entire protocol. You need to. Oh, I see. I guess you can have people getting corrupted later.
Yeah, no. For t is less than n over 4. So if n equals 4, we use the t is less than n over 3 protocol because that's the Hobbit protocol. Yeah. Because n is a Hobbit in that case. Yeah.
Okay.
Yeah. It's only when you have like n equals 40 you use that. Yeah.
So let's do one quick question and then.
Yeah.
First off, I appreciate your commitment to the Lord of the Rings bit. That was very enjoyable. So your benchmarking on decryption was around like 0.6 seconds. How does that compare to non-MPC decryption? Like how much of an overhead is that?
Oh my God, that's like mega. I mean, there's like thousands of times. But it turns out that in the application, this isn't a problem because what we're doing is we're running smart contracts. And so this is, so at 1, that's okay. 2, the FHE operations, which normally everyone goes, that's slow. That's also okay, because you know what's slower than FHE and you know what's slower than threshold decryption? Blockchain. So we're actually deploying, this is the fast bit, and the blockchain is the slow bit, yeah? So it's really, this is not a problem. So we're actually able to reach the kind of transactions per second that's currently on Ethereum. We can, if we have hardware acceleration, this will drop dramatically. And what I should say is that 0.6 per second, that's not the MPC. The MPC bit is like 10 milliseconds, 5 milliseconds. Well, you know, it's basically ping time. It's the speed of light because it really is just send data, a little bit of computation, done. The real bit is you have to do this big FHE operation before, which is costing the 0.6 per second. Once you get hardware acceleration for that, that just drops as well. So that 0.6 will disappear when the hardware accelerators come on.
Okay, thank you. Let's thank the speaker again.